Hello everyone, my name is Kumar Kaithwas and today in this video we are going to take a look over viewing transformations in computer graphics and visualization. So let's get introduced to what is viewing transformation. So viewing transformation refers to the process of converting the coordinates of an object in a real world coordinate system into a display screen coordinate system. So basically, consider any object in the world, in the real world, and we want to display it on a monitor in a 2D format. So basically, converting the real world coordinates of the object into something which you can display on our 2D screen is known as viewing transformation. For example, just like a photographer chooses what part of a scene to capture using a camera frame, viewing transformation helps select what part of a 3D or 2D world we want to display and how we want to display it. The process of viewing transformation involves basically three steps: defining a window in world coordinates, the region of interest, mapping it into a viewport in device coordinates, which is the region on screen, and adjusting the scale orientation and the positioning so that the image fits display properly. On the right hand side you can see the diagram of viewing transformation. Let us consider coordinates of real world object as x, y, z in the x, y and z axis, which is a 3D object. So the first step is modeling transformation, which converts the 3D object coordinates into 3D world coordinates, and then the camera transformation converts the 3D world coordinates into 3D camera coordinates, and then the projection transformation converts the 3D camera coordinates into 2D screen coordinates. Hence you see the final objects in x and y axis, which is the 2D image coordinates, and this whole process comes under viewing transformation. Viewing pipeline in computer graphics. So the viewing pipeline is a sequence of transformation that prepares the project's 3D or 2D world coordinates into a 2D screen space. So basically pipeline is nothing but all the steps we have taken and all the steps we have gone through from converting a real world object's coordinates into a 2D coordinate system which we can view on the monitor. It helps in determining how the objects from the virtual world will appear on a monitor. The pipeline includes several key stages. So the key stages are: the first one is a world coordinate system. This is where the objects are defined. Consider an object which we are having in real life, which that object will come under world coordinate system. The world coordinate systems are the global reference frame in which all objects exist before any transformations are applied. The second one is the camera or view transformation. This is the first step in viewing pipeline. It involves defining the position and orientation of the viewer or camera in world coordinate system. The goal is to position the scene so that it appears from the viewer's point of view, effectively transforming the world coordinates into camera coordinates. The third one is projection transformation. Once the camera has been defined, the next step is projection. In this stage, we define how 3D objects will be projected onto the 2D screen. Continuing the viewport transformation, this stage maps the projected coordinates, which are now in 2D, to the screen space. The viewport defines where on the screen the image will appear and also ensures the image fits in the specified display area. It often involves scaling and translation to fit the image into the monitor's pixel grid. The fourth step is clipping, the process of cutting away parts of the objects that fall outside the viewing window or viewport. Only the visible parts of the objects are rendered. This helps improve the performance by not rendering unseen portion of objects. And the last step is the image is converted into pixels or rasterized, which we will be reading in the upcoming slides, and which is creating the final 2D image that can be displayed on the screen. So this viewing pipeline is basically completely a step-by-step process of how coordinates of a real-world object are converted into 2D coordinates, which one can view on the screen or monitor. So the key points to remember are world coordinates, where the objects exist in the actual scene or actual scenario in the real world. Camera coordinates, transformed coordinates after defining the camera's position and orientation. It is basically the from where you are seeing the object, from which angle you are seeing the object. Third one is the projection, mapping 3D coordinates to 2D screen coordinates. Fourth one is viewport, defines where and how the image fits on the screen, and clipping discards the portion of objects outside the view. Coming over to the World Coordinate Systems (WCS). The global coordinate system is in which all objects are initially defined. Basically, it defines the world coordinate system is it's global. Every object can be defined under this, and it is unique for all the objects. Independent of the viewer or camera position, objects are placed using transformation like translation, rotation, and scaling. It acts as a reference for positioning multiple objects in the scene. Object coordinates are converted from model space to world space using modeling transformations. Coming out to view reference coordinate system (VRC), a coordinate system related to the camera's or viewer's point of view. So basically, it is a coordinate system which is related to the camera or viewer's point of view. Okay, the origin is placed at the view reference point (VRP). The axes are oriented such that n-axis points in the viewing direction, usually negative z-axis. U and V's axis define the view plane similar to x and y, which is very clear. You can see on the right hand side in the diagram. Transformation from the world coordinates to view coordinates involves translation and rotation. Let us now look at perspective projection. So mathematics of perspective projection involves the perspective divide, where x, y, z are the original 3D coordinates and x dash, y dash are the projected 2D coordinates. So basically, how do you get the x dash and y dash coordinates? So we have a formula: x dash is equal to x by z and y dash is equal to y by z. So that's how you can get the new 2D coordinates. Characteristics of perspective projection are: objects reduce in size as they move away from the camera, can be modeled using perspective matrix that involves projection onto the near and far clipping planes. Let us now look over orthographic projection. Mathematics of orthographic projection. The transformation of matrix maps the 3D coordinates directly into 2D. So here we are converting directly converting the 3D coordinates directly into 2D, where x, y dash are the original 3D coordinates and x dash, y dash are the projected coordinates, 2D coordinates. Characteristics are: no foreshortening or size change, commonly used for architectural views, CAD, and technical drawings. Well, let's take a deeper look into the viewing pipeline. So let's now first have a overview of the viewing pipeline. So these are the basic steps that are taken, that are done, that we have gone through uh, in a pipeline. So first step is the model coordinates, then the world coordinates, which are next converted to viewing coordinates, which are then converted to projections, then viewport, and finally we get the device coordinates. Each transformation step brings the objects closer to their final position on the screen. You can clearly see the diagram, and you can take the help of the diagram to understand what viewing pipeline actually is. The main components of the viewing pipeline are modeling transformation, viewing transformation, projection transformation, and viewport transformation. And after viewport transformation, you get the final 2D coordinates of the real world object in the 3D real world, which you can view on the monitor. Next topic is view frustum. The view frustum is the region of space that is visible to the camera. So we are looking from the camera's perspective. So view frustum is nothing but the region of space that is visible to the camera. It defines the boundaries of the camera's views with near and far clipping planes. Frustum clipping is something which is known as objects outside the frustum that are not rendered. Also, basically, if you are taking look at an object from a camera's perspective, it basically forms a frustum. So that frustum is known as the view frustum, and everything outside that is known as frustum clipping. Clipping algorithms ensure that only visible objects are drawn. Now, what do you mean by clipping? Clipping is the process of removing parts of the object that fall outside the view frustum. So basically, when you are looking from a camera's perspective to a real world object, it basically forms a frustum. So everything which is falling apart from the frustum are rendered outside and are cut short. So that is basically known as clipping. There are multiple types of clipping. Point clipping, which is determines if a point lies inside or outside the clipping area. Line clipping, clips lines against the boundary of a view frustum, and polygon clipping clips polygons that extend beyond the viewing area. Viewport transformation. Viewport transformation is nothing but mapping the 2D projection coordinates to the actual screen pixels, which involves scaling and translation to fit the image onto the screen. So basically we are fitting the image onto the screen properly. Mathematics, there are some mathematics which is involved here. We have used some formulas. The viewport transformation uses the screen's resolution to scale the 2D coordinates, and the formula is x dash is equal to x minus x minimum by x max minus x minimum multiplied by x max minus x minimum plus x minimum. Also, y dash is equal to y minus y minimum divided by y max minus y minimum multiplied by y max minus y minimum plus y. Now let us look over the real world application of a viewing transformations. So where is viewing transformation used and how it is useful in the current scenario? So computer aided design CAD. Accurate technical drawings rely on both orthographic and perspective projections. Gaming and simulation, realistic rendering video games use perspective projection to create depth. Virtual reality VR, as we all know, is the trend these days. VR applications use viewing transformation to stimulate an immersive environment. Film and animation. Movies and animation use complex viewing transformation to create 3D scenes. So let us move on to the conclusions. So viewing transformation is essential for converting 3D data into 2D image, critical for computer graphics in various fields. Understanding the different types of transformations and projections ensures realistic visualizations in virtual environments, designs, and entertainment. The key concepts are coordinate systems, transformation matrices, projections, and viewport transformations are the backbone of modern computer graphics. Let's summarize it. Viewing transformation enables the rendering of 3D scenes onto a 2D display. It involves several transformations such as modeling, viewing, projection, and viewport. Projections can be orthographic, low depth, or perspective with depth. Real-world applications include CAD, gaming, and virtual reality. These are the references from where the PPT is made. Yes, thank you.